Hello everyone. This week we will be talking about the root locus plot. Um, we are given a system, a high order system, fifth order system in this case, and the first task is to calculate the root locus of the system using our locus and plot the poles manually. If you remember, we had a week where we were concerning about the body plot, the root locus plot, and also the step response, ramp response, and impulse response. The second task was actually covered there, but I'll still go through it. So it's basically the repetition of A using the symbolic toolbox rather than the root locus command itself. And in C, the third task is to just use subplot and different K values and mark the poles and also plot the step responses so we can kind of look at the problem visually and conclude which K value results in what behavior. So let's start off with A. Let's look at the root locus plot of this system. Now, as you already know, we can use our locus as the command, and if we run this here, we'll get a root locus plot. So that's nothing new. But once this actually shows up, I'm going to show you that the root locus, our locus command here, it has more capabilities. It's just not for visuals and generating visuals. It can also provide you the data that you are looking for. And if you wish, you can also plot it on your own. So this is the root locus plot of the system, which we will dive in deep later. But if we look at the help our locus, if we get help from MATLAB, hopefully, there we go. Now this is the connection. Here we have this R, K syntax here, where R stands for the roots, K stands for the gain values. So what we can do is we can just get the roots and also the gains. So let me call them poles because we're considering a transfer function. Poles and gains. So if we call it like this, you'll see it outputs this structure here. So first of all, let's look at the size of the poles, 5 to 56, and let's look at the size of gains. It's 156. So we have basically 5 poles because the system is a fifth order system. We have 56 different K values or gains. Therefore, we have 56 different set of poles. Therefore, we can just look at the or use these variables in order to create our own plot. Or if we are searching for a certain set of poles, then we can just do it by using these poles here. So let's actually look at poles and the first 3 columns. Now we can see that we have basically -4, -2, -2, and then a complex conjugate pair here. So each column stands for each gain value. So if we look at gains 1 to 3, we'll see that if we have K0, these are the poles. If we have K, the next value, which is again close to 0, then we have this here, and it goes on like that. Now, if we are plotting the root locus plot, if we want to generate it ourselves, let's also have hold on. If we want to plot it ourselves, what we can do is we can just use each row to plot a certain line, because each column corresponds to a different K value, and the root locus plot on its own is basically the path that a pole takes when we are increasing k, starting from 0 up to infinity. So therefore, this is basically stored in the first row. What we can do is we can just use that data. We can just use the first row for the first pole, -4, the second row on its own, the third, fourth, fifth, up to the nth row, because we have n poles here. So it's quite easy to recreate the plot itself, and the reason why we do that is basically because of the MATLAB's built-in root locus plot is not really that customizable, and you will see what I mean by that, because I want to change, sometimes I want to change almost everything in order to create more effective visuals. Therefore, I might take the manual path, and that's also the reason why we are given this opportunity where we can just extract the poles and gains separately. Or if we have the theoretical knowledge, we can also do it using the symbolic toolbox. But here, the rlocus command is actually sufficient and more than enough. So, basically, I'm going to just write down plot, and what I need is I need the poles, I need the first row for the first plot, and all the columns. Now, of course, this is a complex number, a vector of complex numbers. So I need to take the real part here in order to have the x-axis, and I'm going to just copy and paste it to get the y-axis, because the imaginary part is the y-axis, and let's assume that this is a black color, and let's increase the line width. So, therefore, x label is going to be sigma, the real part. Y label is going to be j omega, and the title for now will be root locus plot. So let's try this out. Yeah, it should work. There we go, it's a straight line. Of course, this being a straight line seems a bit awkward, but it is the pole at -4. If I zoom in here, I should get -4. Because the root locus plot goes up to gain infinity, it kind of tends towards the left here. So of course we are not going to do this for only the first one. First of all, we need to get the order of the system. You might want to use gs dot denominator like this, and then just take the length of this vector and then -1. This would work. As you can see, it's n equals 5 because we can use the direct dot operator here. GS is kind of a struct here, and you get the denominator. You can also get the numerator and extract all the unnecessary cell structure, basically, because it could be a MIMO system, therefore it needs a cell struct. You can get rid of that by using this here, and then -1 in order to get the order here. Or, since we have the poles here, and we know that the size of poles will give us this data here. If you use size a certain matrix, comma 1, it means that this is the first dimension, so amount of rows. If we use basically 2 here, it will give us the second dimension, which will be the columns in this case. But I'm interested in how many rows there are, because each row corresponds to each pole. Therefore, I'm just using size poles, comma 1, which will give me 5. So this will help me in creating this for loop here, starting from 1 up to n. And then, of course, instead of using 1, I can use these indices here, and I don't want to provide a color because MATLAB should choose its own color. So if I repeat this now, you can see that we have this nice plot here. You might argue that this doesn't look like the root locus plot, but if you zoom in a little bit, you'll see that this is basically a root locus plot. If you zoom out, you can see that the asymptotes are basically at work here. So if we zoom in a little bit or provide the k-vector ourselves, that wouldn't be the issue. So the thing that is missing here is basically the open loop poles. We should place crosses. So what we can do now is gain starting at 0 always. I'm not sure. Let's see. Gains, the first value 0. So we could safely assume that this first one could be used here. So let's plot the, let's actually get the same here. But instead of doing this, let's get the first one here. And then the first one here. And let's try this basically. Of course, what we can do is we can just use again I in order to generate this. Let's see. Because for each row we will just get the first one here. Oh, we again did it. This should be 1 here. We're just looking for the first pole. We take the real imaginary values. Since it is going to be a point or it's going to be a cross, we're just giving it a marker and a black color, so we get the open loop poles here. So let's see. Yeah, it didn't work. Of course, the reason being that it should be the ith comma 1, because we're interested in the first column only, and it will be the ith row. So my bad. So now it should work. Let's see. Looks quite more like it, I would say. So what we still can do is we can still improve on this. First of all, we don't have actually this grid stuff going on here. What we can do is we can just add the grid manually, or we can use the sgrid function. So the sgrid function actually takes zeta and omega n values. So we could just come up with 0, 0. Let's say 2, up to 1, and then omega n values from 1, or starting from 2 up to, let's say, by 2 increments up to 10, for example. I don't know. So it has a more professional view here. But we need to zoom in order to get this effect that we're looking for. So something like this here. There we go. Now these are actually half circles here, but it doesn't feel like that because of the aspect ratio. And as far as I remember, I am going to try this for now. Axis equal kind of solves that issue as far as I remember. So let's see if it does. So it has kind of this new aspect ratio here where we can see that there are indeed circles. And here we can see that there are certain omega n values, and then we have the zeta values here. And if we want to choose a certain dominant pole pair, this will be our point of interest or domain of interest. And we can just choose certain zeta values. There's a limit to this because of the specific system that we have at hand. Now, of course, the capability of clicking on a certain line and seeing what the gain is, we have lost that. That is for sure. But we have plotted our own root locus plot here, which gives us hopefully a better understanding of the root locus plot, because it is basically, at the end of the day, it's just a path of poles when we change a certain gain. So let's actually go to the symbolic toolbox and let's repeat that part here so we get a better understanding. Now, let me just copy and paste this. Of course, we don't have this part yet, so I'm going to comment it out and also comment this part out. Now, first of all, let's convert it into a symbolic expression here. by defining it 3 divided by s to the power of 5 plus 9 times s to the power of 4 . There we go. Now, what we need is we need a k value, which is going to be a real value, and our closed loop is going to be the following. So let me also sketch that in order to remind you that we have actually this feedback loop here. And we're interested in the overall closed loop here. So it is important to note that. So before this, we had GS, or the open loop poles are basically the poles of the system under control or the plans. And then we have a static gain. We place it in a unit feedback where we have a minus sign here. So we're basically measuring the output. We have a certain input in our mind. We take the difference. We take the k times that difference or the error and apply it to the system so that we can adjust the output. We are trying to regulate the output. And at ideal conditions, what we want to get is basically reference tracking. This is called reference tracking. If we apply a certain input value, the output value should eventually reach that value and follow it. So this is basically our aim here. And this root locus plot here helps us out in determining whether it is going to track or not, and how it is going to behave during the transients, because, well, transients are a thing. We have a dynamic system, we apply a certain change to the input, and it will have effects. So, therefore, our closed loop transfer function is quite important, and the pulse of that resulting closed loop transfer function is at interest. So, what is the closed loop? Well, the closed loop is k times GSS, and 1 plus divided by 1 plus k times GSS. Now, since we are dealing with a p-type controller or a gain, and the system has no zeros, we can skip this part here. We're only interested in the denominator here. We can use num then, and then TSS, and we will have a certain polynomial here. Now, here what we are going to do is basically we are going to choose a certain k vector here, different values for k, and then we are going to substitute that and then we will calculate the roots. So what we can do is we can just define a k vector here. Let's start from 0, 0.1 up to 0.3, and we need basically the poles here. So you kind of see that we are preparing this gains poles thing, so let me call it gains. And how many poles will be there? So first of all, since we have the denominator here, and I did this actually by using gs.denominator and then the length of that minus 1. Here, since we're in the symbolic toolbox, what I'm going to do is I'm going to take the coefficients of the characteristic polynomial in this case, look for its length, and then minus 1, because we will have, as you can see here, we have a constant term and then 5 more terms. So the order is 5, we will always have a constant term, so we have to subtract 1 in order to get the order here. So we will kind of follow the same scheme here, where we have n rows and then the length of gains columns, and we will set up exactly the same data here. So for I equals 1 up to length of kvec here, and then we can acquire the k value, kvec I, of course we have to substitute this into PCS. Instead of K, we will have K-val here. And at this point we can again use the coefficients here and then the roots command, or you can just use solve coefficients of pole and then the roots of that. This will basically give us a column vector of the roots. So we are already interested in the column vector. So I'm just going to use this. And it will be all the rows but the ith column. So we can get the data that we are looking for. So poles. As you can see, we have 56 poles. Oh, let me run 2 basically. I'm running run 1. And yeah, it should be gains. Gains. There we go. Now we have our poles. As you can see, it's basically the same data, but with our custom gain vector. Now, we have to change the gain vector a little bit. We should increase the interval of that. But if we do it linearly, if we just increase it up to, let's say, 100, it will not be ideal because this will be linearly stepped, but we want to reach basically, theoretically, infinity, but that's not possible if we do it like that, and if I add more and more zeros, it will just become slower and slower. What I can do instead of doing that is I can use log space logarithmically. I might space it, and I might just choose 100 points, I don't know, maybe 40 points, just less points, but the gain values will grow faster and faster. You can see it is 10 to the power of 3, whereas we start with different values. Let me show it like this maybe, or even with VPA in order to show you that we start at low values. We have all the low values here, and then it kind of grows and grows and grows up to 1000. And this wouldn't be possible with 40 points if we didn't use log space here. Since we have done this part here, we have basically replaced this locus command here. We can create the same plot as usual. But we have a slight issue, I guess. Why is that? Let's look at the poles here. So I don't know if you can see it, but we have a slight issue here, and the issue is the following. Since we have this complex conjugate, for example, and it was also visible here, the overall root locus plot might be correct on the real axis, for example. -4 goes to the left, that's correct. But there is an issue where we have a sign change here. This pole didn't jump to the positive one here. It should basically jump to this one here. So, and then again, this stays positive for some roots, and then here we again have a minus sign. So you have to associate which pole is moving to which point, and which point is basically the closest to the pole that you had calculated previously. So what I mean by that is I have -5.9457 here. Which one of the next poles or the previous ones belong to this pole? Which is actually the next value for this pole out of these poles here? So luckily, if it's a real value, you can see it is basically -5.94, and then this is -6. So this is basically correct in this path here. You can see -6, it's always correct here. But the complex conjugates may mess this up as it is now. that means that we have to do something else. What we have to do is we have to basically sort the values. And how we need to sort that is basically the question here now. And yeah, we have to sort them. So how can we do this? Well, when we are assigning the poles, we have to sort the result here. Where is it? Here. It seems like, and it is obvious that the our locus command here does the job for us. So if we are doing it ourselves, we have to sort it ourselves, which is quite a bit annoying, but we have to deal with this problem here. So what we can do is we can just use the sort command. We have a sort command here available. And there are some options. And as far as I remember, we needed to sort based on the real values. So it is kind of the comparison methods and then real. So let's try that out. So sort and then comparison method and then based on the real values, as far as I remember. So let's run this again. We messed up for some reason. Comparison method. Maybe I should convert it into a double here, if it's not. So let's see if it did the job, and it did the job. And if we look at the poles now we can see that the signs here, you can see we have the real value, and then we have -3 minus. And the reason for that is that if we just sort it by the real, or compare it by the real value, the negative ones are basically less than the positive imaginary parts, so it's kind of aligning the minus signs and plus signs accordingly, so it does the job. It is a quick trick that we need to know, of course. If you're trying to implement stuff yourself, then sometimes you have to come up with workarounds, and this is again one of those times when you have to just use some sorting and then comparison method real in order to just get rid of the problem. Of course, for the root locus plot, we can just get away with this sorting stuff, but if it would have been a different case where we have to associate the poles, this might not work, because we know that each pole or root on the root locus has a continuous path, and I can therefore use this ordering stuff, but it is not applicable to all pole association problems that you might encounter. It's just for the root locus plot. In case you might want to use it elsewhere, you have to be careful. So we basically have now the root locus plot. Let me just show it again. This is our nice root locus plot where we have again the same the ordering. We have also an x is equal here, as far as I remember. So yeah, this is the root locus plot. Now what we can do is we can choose different k values in order to show what is really going on here. What k value corresponds to what set of poles, and then how it also looks like when we have the step response of the closed loop. So I'm going to just create a subplot at this point. Let's have 2 rows, 1 column, and the first one of that is going to be this here. Let's call it AX1. Let's create another subplot. This time around it's going to be time. It's going to be YT. And we'll call it step response. So, of course we're plotting on AX1, 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 and I guess, I'm not sure, this should be it. So let's run it. One more time. There we go. Now, of course, changing the aspect ratio is kind of going to be a trouble, I guess. So let me just remove this for now. So let's see, that's more like it. Now, what we want to do is we want to basically have different k values. So for example, we have the root locus plot here, there's no problem. We can do it somewhere here. So let's have k1 for example, and let's say it is going to be 20, and let's have k2, and it is going to be, let's say, 100 for some reason. So what I want to do is I want to just basically look at the step response, and I also want to look at the pole spread so I can see what's going on. So yeah, let's have ts1 and then use the feedback command, and then k1 times ts, comma 1. This is basically our closed loop here. And what we need to know is we need to find out the step response here. Let's call it y1 t1. And we also need the poles, zeros, pz map, ts1. And then we are just going to plot basically on AX1. What we need to plot is the real values of poles and the imaginary values of poles with a marker of this, with an X, with a color that should be red, for example, and line width 2. So, and then what we're going to do is we're going to plot on AX2, which is going to be basically the graphic here. We are going to plot t comma y and then the line width 2, and of course the color red. There we go. Now we're basically going to repeat this thing for 100 here. So let's copy and paste it here. ts2, k2, and then ts2, y2. Oh, this is t1, y1, t2. This is going to be 2 again. I didn't plot the zeros because we don't have them, but you get the idea. And this should be it basically here. So let's just run it and see if it works. So, yeah, 100 is an overkill at this point because it just both of them are not stable. We can see that, but you can see there's too much color here. What we can do is we can just change that. We can come up to here and assign the value black in order to get basically a clearer view here. First of all, that looks better if in terms of visuals. So let's choose a lower value and maybe a value of 20. Still not getting what we want, but I guess this one should do the trick. Yeah, and let's choose 30 seconds of settling time here, so we have basically final time here, so we have them aligned. And there we go. Now what we can conclude from this plot is the following. For this system especially, we can see that the choice of red, which was a, by the way, we can also show the values here. I didn't do that. Let's have hold on and then legend show, and we can give them display names here. Display name, and then maybe directly num to strk1 here. So this one should k2. Of course, you can see that we can define a k vector again here, the values of interest, and use a for loop in order to generate this automatically by assigning certain colors, but I'm going to skip that part for now. I guess I wanted to put grid on here, not hold on. And that's basically it. You can also go ahead and add some settling time overshoot values here, or the zeta values, whatever. You can just put in more data, more informational data as you wish. Now, what we can conclude from this is the following. For this high order system, these two poles are basically the dominant ones because they are closer to the j omega axis. And if we have a low value of k, we can see that, for example, we have a higher value of zeta, which means that the red one here is going to have more friction because that's the damping ratio. Zeta is the damping ratio, and the higher the damping ratio, the higher the friction, the lower the oscillations. So we can see that it's not oscillating that much. It has a low steady state value, and it's kind of faster than the blue one here. It has a lower settling time value. Now, if we increase the gain a little bit for this system, we have higher oscillations, and the reason for that is we have lower friction. As you can see, the damping ratio is lower, the friction is lower, therefore the oscillations increase. If this is a mechanical system, for example, this would be the comments that I could have made about this. It has low friction, it is oscillating too much, and you can also see that this is a slower setting down, or kind of transitioning into the steady state way later. It's not even in this frame here, so it's becoming slower. Even though some poles are moving to the left on the left hand side, those don't really matter at this point, and these ones are basically dominating the behavior. And yeah, seeing what really happens here is quite important. If you think about the controller synthesis, the root locus plot here can give you an idea about the overall closed loop, how it's going to work, and what gain causes what. Of course, this is just basic root locus and basic controller tuning. And the most basic controller, that is called the p-type controller, which is basically or practically a gain only. This is basically what we can do here. We can do more stuff, we can just show more visual data about this, but this is sufficient at this point. This is a basis for controller design. We have a course for that, control system design, and there we are also adding some poles and some zeros and some control structures in order to see what's really going on, how we can change the behavior, or how can we influence the change in what way. So we've talked about the root locus plot. Hope that you have a better and deeper understanding about the root locus plot, how it's generated, and for some systems it is important to see what the effect is. Sometimes some students like to just assume general stuff and just memorize it and go on with it. One of those things is basically if you increase the gain in a certain closed loop where we have a p-type controller, if you increase the gain, then the system becomes faster and becomes more stable. As you can see, this root locus plot here proves the inverse. You can see increasing the gain for this system is not good at all. So coming up with general statements is not always true, doesn't hold. We have to examine the root locus plot in order to conclude such things. So this is basically it for this week. See you in the next lecture.